Welcome back to the Explainer Focus Learners. I am absolutely thrilled to have you here today because we're looking at a genuinely fascinating piece of engineering. We spend so much time talking about how to make our technology more durable, more permanent, and frankly, way more expensive. But today, we're going to completely flip that script. We're looking at a concept that revolutionizes drone design not by making it indestructible, but through a brilliant structural innovation that actually embraces disposability. Okay, let's dive right into this. I want you to take a second and completely rethink your entire philosophy of manufacturing and value when it comes to unmanned aerial vehicles, UAVs. What if the future of drones isn't about building them to last, but building them to lose? I know, it sounds totally counterintuitive, right? Like, why on earth would an engineer design something specifically to be expendable? Well, to understand the sheer brilliance of this approach, we first have to understand the massive headache that traditional drone operators face every single day. So, let's start with Section 1, the drone dilemma. Before we get into the solution, let's just ground ourselves in the very relatable frustrations of conventional drones. Because, let's be honest, the technology we currently rely on, it's far from perfect. Conventional drones essentially operate as flying blenders. They've got these exposed, high-speed rotating propellers that pose very real safety risks to the operators and anyone standing nearby. On top of that, they have a really loud, obnoxious acoustic signature that severely limits their use in sensitive or urban environments. And if you crash one, oh boy, you are looking at incredibly high maintenance and replacement costs. Now, contrast that with our ideal drone. We want something shielded and safe, quiet enough to fly around a city, and most importantly, so incredibly cheap that losing it isn't a financial disaster. We want it to be expendable.
That brings us to Section 2, meet the MAR11 prototype.
To tackle those massive drone dilemmas we just talked about, engineer Mario Arturo Ruiz Estrada developed a highly experimental solution back in 2016. And what's really interesting about this blueprint is its sheer simplicity. This is the MAR11 drone. It's a 500 by 500 millimeter quadricopter, so a little over 1.5 feet wide. It completely ditches the exposed arms of a standard quadricopter. Instead, all the vital electronics, the flight controller, the battery, the electronic speed controllers, they're all housed right in the center. And the entire propulsion system is surrounded by a continuous outer wall. It's this elegant, box-like structure designed specifically for protection and noise reduction, operating on a standard 2.4 gigahertz radio with about a 12 to 18-minute flight time. To fully appreciate that design, we really need to look at the exact parameters Ruiz Estrada set for himself. The MAR11 was built around 5 very specific engineering objectives. First, protect the propeller system from collisions. Second, reduce acoustic emissions during flight. Third, develop a low-cost disposable platform. Fourth, simplify maintenance and component replacement. And finally, number 5, do all of this while maintaining acceptable flight stability and maneuverability. Because obviously, if it can't fly right, none of the rest of it even matters. And here is how those high-tech engineering objectives translated into the physical world. Check out the functional MAR11 prototype. Notice the materials here. We aren't looking at aerospace-grade carbon fiber or expensive milled aluminum. Not even close. This structural frame is built using lightweight foam board and light composites. You can clearly see the central electronics compartment and the integrated landing supports holding up that distinct external frame. By using modular components, some hot glue, epoxy, and zip ties, the designer created a platform perfectly suited for low-cost manufacturing and rapid testing. Literally, off-the-shelf simplicity.
Moving on to Section 3, engineering a quiet shield.
Let's delve into the actual mechanics of this drone's most distinct feature, because that foam board box, it's actually a highly functional piece of engineering. The crucial point is the external frame itself. It acts as a literal physical barrier. Remember those flying blenders we talked about earlier? Well, this simple structural frame directly solves that safety risk. By physically shielding the fast-spinning blades from accidental contact with walls, tree branches, or people, it massively reduces the probability of catastrophic damage during an operation. If it bumps a wall, the foam frame takes the hit. The propellers just keep on spinning, and the drone stays right there in the air. But it goes way beyond just physical safety. The acoustic mechanics of the MAR11 follow really clever 3-step breakdown. Step 1. That surrounding frame acts as an acoustic shield, physically blocking a portion of the sound waves generated by the spinning blades. Step 2. The structure actually redirects the airflow around the propeller system. And Step 3. As a direct result of all that, direct noise propagation is reduced. Now, while it wasn't measured with high-end acoustic instrumentation, real-world flight observations confirmed a noticeable modification and quieting of the drone's sound profile compared to an open propeller design, and that is absolutely huge for urban operations. All right, Section 4, the disposable paradigm. Now that we understand the physical design, we need to talk about intentional disposability. And I want to be super clear here. When we say disposable in the context of the MAR11, we are definitely not talking about cheap, single-use plastic waste meant for a landfill. By definition, the disposable UAV concept emphasizes extremely low manufacturing costs, the ability to rapidly replace units after damage, absolute simplicity of assembly, and scalability for multiple unit deployment. Economically speaking, it means creating a tool that is cheap enough to be sent into highly hazardous missions where recovery might literally be impossible. Think about it. If you lose a $5,000 drone, it's a disaster. If you lose a $30 foam board drone, it's just a minor line item on a spreadsheet. Which brings us to Section 5, real-world applications. So where exactly does a shielded, disposable drone actually go? Let's see how this builds from a theoretical concept into reality. In the lab, it might look like a modest science project sitting quietly next to its controller. But deployed in the real world, its true potential is obvious. Picture it flying high over a dense city skyline at sunset. Because it's shielded, it's actually safe to fly over populated areas. Because its acoustic signature is modified, it won't disturb the urban environment below. This leap, from a foam box on a lab table to a safe, quiet eye in the sky over a city, is exactly what this engineering philosophy enables. To connect this right back to real-world utility, let's look at the ideal deployments for a platform like the MAR11. Imagine sending a drone into a burning building or a chemical spill for hazardous area surveillance. If it melts or gets destroyed, you just grab another one off the truck. It's absolutely perfect for disaster response and search and rescue, where flying conditions are treacherous and totally unpredictable. It's also highly viable for environmental monitoring, deep in dense forests, low-cost agricultural inspections over vast farmlands, or even as an expendable platform for experimental flight research in university settings. In all of these scenarios, the low-cost disposable frame provides a massive strategic advantage over risking a conventional, super expensive UAV. Which brings us to our final thought for this explainer. The MAR11 proves that sometimes the absolute best engineering solution isn't adding more complex, expensive armor. It's using smart, simple design to make the technology cheap enough to lose. So I want to leave you with this question to chew on. What other expensive, precious technologies in our modern world could benefit from this exact same disposable, low-cost engineering philosophy? Where else are we over-engineering when we should really just be simplifying? Thank you so much for joining me for this deep dive, Focus Learners. Keep asking the big questions, and I will see you in the next explainer.